Hello everyone, welcome you all to the course of Computer-Aided Design and Analysis. In this presentation, I'll discuss Module 5, Part 1 of the presentation. So in this module, we cover the introduction to finite element method, or we call it as FEM. And the detailed course on FEM is offered in the next semester as an elective. So if you get interested from this course, then you can take up that elective course and get detailed or advanced knowledge on FEM or finite element method. So basically, a finite element method is used when you want to solve problems which relates to some complex shape or arbitrary shape. Then when you want to solve problems like using or on this complex shapes, then you might have to divide this complex shape into a finite number of elements. So we will divide the entire geometry into finite number of elements. Then we will solve for each individual elements. Then we will combine all these elements together. Then that will get you the result, or that will solve you the problem on the complex geometry. So basically, all these problems or most of the engineering problems deals with ordinary differential equations or partial differential equations. And the solution of ordinary differential equation or PDEs are easy when the problem is very simple in nature. But if you have complex geometry or complex phenomenon there in the problem, then the solution or the analytical solution of these differential equations will be very difficult, and it will be very time consuming. So we can rely on approximate methods, and this finite element method is kind of an approximate method to solve the problems, and we can get to the almost an accurate result with the help of this finite element method procedures. So as I put it here in the slide, many physical phenomena in engineering and science can be described in terms of PDEs or ODEs. And in general, solving these equations by classical analytical methods for arbitrary shape is almost impossible. Therefore, the finite element method or FEM is a numerical approach by which these PDEs can be solved approximately. As I said in the previous slide, FEM is a numerical method for solving problems of engineering and mathematical physics. And the finite element formulation of the problem results in a system of simultaneous algebraic equations for solution rather than requiring the solution of differential equations. So what we do here is that we will convert the algebraic equation or the differential equation into a system of algebraic equations, like we did in the case of finite difference method that you studied in the last semester during the fifth and sixth module of your course on computer programming and numerical method. There we generate the equation or the algebraic equations for Laplace equation, and we solve the problems using finite difference method in there. So similarly, here also we can convert the problem or the differential equation into algebraic equations, and we can solve the algebraic equations by Gauss elimination method or Gauss Seidel method. Then we can find out the solution of the problem. So that also I have studied there in the last semester. So as an engineering point of view, we can apply this FEM in many areas, such as for finding out the stress analysis. So the primary unknown while we deal with the stress analysis would be the displacement. Then we can find out the strain, and once we have the value of strain, then from the stress strain relationships for the problem, we can find out the stresses. Then once we get the stresses, when we can analyze the problem that where in the member we get the maximum stress, and where in the member the failure can happen or failure will begin. So similarly, this FEM can also be used for solving problems related to heat transfer and fluid flow and electromagnetics by computer simulation. So these are the main applications area where we can apply this FEM tool for solving problems. So let's see into the details of finite element method. So as I said, this is an introductory course. So it covers the basic idea about how to solve problems using this finite element techniques. So for that, let's discuss which are the basic steps which we have to use for solving problems on finite element method. So this basic steps are common whether it is a problem related to stress analysis or heat transfer. The only thing that differs in all these areas are the governing equations. In the case of stress analysis, we use the Hooke's law and the strain displacement relations. But when it comes to the heat transfer, we use different sets of equation and so and so. So basically, the steps are the same, but the equations used are only different. As I mentioned in the introductory slides, uh, it's difficult to use or difficult to solve the complex problems or the problems which involving complex shapes using the analytical methods. So we go for the finite element method. So wherein we divide the problem into finite number of elements and we solve each element, then we combine together and we get the final solution. So to begin with the steps of FEM, the first is the discretization and the selection of element type. We will see one by one in detail in the coming slides. So first, let me go through the steps which involved there in the solution of FEM. Then select a displacement function or interpolation function or the shape function. Then define the strain displacement and stress strain relationships. Uh, Here in this particular course, we deal mostly the problems related to structural or mechanics of solids. So that's why I've mentioned strain displacement and stress strain relationships. So if it is related to heat transfer or fluid flow problems, then we have to use the respective relationships corresponding to that areas. Then once we have the relationships, then we can derive the element stiffness matrix and the equations associated with it. So this is corresponding to a particular element. Then once we have the element stiffness, then we can assemble all the element stiffnesses or stiffness matrices. Then we will get the global stiffness matrix. And we can apply the boundary conditions there in that global stiffness matrix or the global equations. What it then we go for the solution of the unknown, and generally the displacement is the unknown in the case of a structural problem. Then we can once we have this the primary unknown, which is displacement, then we can find out the secondary unknowns such as strains and stresses. Then once we have the values of strains and stresses, then we can interpret the results graphically as well as with the help of the numerical values. Then we can analyze where the failure can begin and which are the areas where the stresses are maximum, etc. So now let's move on to see what is the meaning of discretization and select the element type in the coming slide. So as I mentioned in the previous slide, the steps involved in solving a finite element problem is common regardless of the domain of the problem. So here, let's see first what is the discretization and selection of element type mean. So let's understand the meaning of this with the help of a simple example. So here I have a circle and I need to find out the circumference of the circle. And we know that we can find out the circumference of the circle using the analytical formula, which is 2 pi into radius of the circle. So that is analytical solution. So if I have the value of the radius of the circle, then immediately I can find out the circumference of the circle using that formula. But what if I don't have a formula for finding out this, the circumference? So the one of the way for solving or finding out the circumference is that I'll divide this circle into a number of pieces or number of elements. So here what I have done is I've divided the circle into 5 number of elements of equal length. Okay, and here I divided the circle into again 5 elements, but they're of unequal length. And these elements are joined at a point called node. So these points are called nodal point, where the elements connected to each other. And here, once if I know the length of a particular element, then for example, this case, let's say the length of this particular element is 2 centimeter. then the total length of these elements would be 2 into 5, that is 10 centimeter. Then I can say that approximately the circumference of the circle is 10 centimeter. So if I divide the circle into a more number of elements, let's say instead of this 5 number of elements, let's say I've taken 10 number of elements. So that fit in maybe more better than the element of this particular length. Then I'll get the circumference of the circle, or I will get the result which is more close to the analytical solution. So depending upon the problem, you can increase the number of elements that you need to choose for solving the problem. So that is what the discretization means. So you are dividing your geometry into finite number of elements. So that is called discretization of your geometry. So if you have a complex shape, then you will understand it. Like it's not that easy to find out the circumference of your geometry with the help of a simple formula. So in that case, what you can rely on, you'll divide that into finite number of elements, and you can find out the circumference, for example. Similarly, let's say the displacement or stresses or strains, whatever it is. So let's go through the slide. Then it means that it involves dividing the body into an equivalent system of finite elements with associated nodes and choosing the most appropriate element type to model most closely the actual physical behavior. Uh, so what it meant by the second part of the paragraph is that we have to choose the most appropriate element. For example, here I've chosen a linear element for dividing this circle. Instead, I can use a cubic element or a quadratic element for dividing the circle. So if I increase the degree of the polynomial, then I will get more accurate result. So that is the meaning of this most appropriate element type. So you'll understand more on the type of element in the coming slides. So for the time being, this is what I meant by this sentence. So you can, instead of a linear element, you can either go for a quadratic element or a cubic element, or even a higher degree polynomial element. Then you will get to the more accurate result. Then the total number of elements used and their variation in size and type within a given body are primarily matters of engineering judgment. So if I need a more accurate result and I can compromise on time, then I can divide this into maybe 100 number of elements. So that will increase the accuracy of my problem. So that all depends upon the judgment of the guy who is doing this particular problem. And as I said, the elements must be made small enough to give usable results and yet large enough to reduce the computational effort. Okay. And domain is represented as a collection of finite number of subdomains, namely the line segments. So each element is a line segment, and this is called discretization of the domain. That means we are dividing the entire domain into n number of subdomain, and that process is called discretization of the domain. And each subdomain or the line segment is called element. That means each of the line segment or each of the subdomain is called an element. Then the collection of elements is called finite element mesh, and the elements are connected to each other at points called nodes. We have seen that in the previous slides with that problem of finding out the circumference of a circle. So now you have understood what is an element, or what is a discretization, what is an element, and what is a finite element mesh, and what is a node. And these points are, or these terminologies are very important in FEM point of view. So understand clearly before going to the next slide. And we know that once we discretize the complex geometry into finite number of elements, we have to choose the appropriate element for that. So we have a number of elements, and here right now I'm listing only some of the important ones or some of the commonly used types of elements. So here the first of them is a one-dimensional line element. Basically, the bar element and beam element are considered to be one-dimensional elements. And these elements are commonly used for modeling of trusses and frame structures. And we know that commonly a bar element is used for modeling of trusses, and beam element is used for modeling of frames, because we know the basic difference between a bar element and a beam element, right? Or a bar and a beam. The bars are commonly used for taking up the tensile load, and the beam can resist both axial, lateral, and twisting loads. So, a truss, as I said, a truss is an assemblage of bars with pin joints, and a frame is an assemblage of beam elements. So here, this is an example of a two-noded, or this is a two-noded line element. This can be used for representing a bar element as well as a beam element. So here, this is a higher order line element which is having three nodes, having two nodes at the ends and one middle node. We can even have more number of nodes in between the end nodes. And similarly, we have two-dimensional elements. Commonly used two-dimensional elements are triangular and quadrilateral elements. These two-dimensional elements are used for solving plane stress and plane strain problems. And we can also have higher order two-dimensional elements, such as this one, which is a six-noded triangular element. Uh, we obtain this six-noded element by adding nodes or mid nodes in between this side nodes. So here also we have an 8-noded quadrilateral element. This one we obtain by adding mid nodes to this quadrilateral element. So these are the one-dimensional and two-dimensional elements. Commonly used three-dimensional elements are tetrahedral and hexahedral elements, and they are used when it becomes necessary to perform a three-dimensional stress analysis. The basic three-dimensional elements have corner nodes like these ones, and straight sides. And whereas higher order elements with mid-edge nodes have curved surfaces for their sides. For example, this is an example of a higher order tetrahedral element, and this is also an example of a higher order hexahedral element. So here we are having nodes or mid nodes on the sides, and here we have curved edges or curved surfaces. And here we have axisymmetric elements, and these are used for axisymmetric problems. And these are formed by rotating a triangle or a quadrilateral about a fixed axis located in the plane of the element through 360-degree. For example, this triangular ring element is formed by rotating this triangular element with respect to the z-axis through an angle of 360-degree. And these axisymmetric elements are used when the geometry and the loading of the problem are axisymmetric. Now, the second step in FEM is selection of a displacement function. So, by choosing a displacement function, we can represent the variation of field variable within the element. So, in the case of structural mechanics problem, the field variable is displacement. So here we can find out how the displacement varies within the element. So we can represent the variation of displacement either with a linear equation or a quadratic equation or a cubic equation depending upon the nature of the problem. So let's say that if I choose the variation of displacement with the help of linear equation, let's say y equal to or u equal to a plus bx. So in that case, I'm assuming that the displacement is only in the x direction. Then I can find out the values of the coefficients which are like a and b. So once I have the equation which is having the value of a and b, then I can find out the displacement at any arbitrary point within the element. So that's how I establish a relationship between a displacement and displacement at a particular point within the element. So again, we can use a trigonometric series also for representing the variation within the element. And if we have a two-dimensional element, then we know that we'll have displacement both in the x and y direction. So in that case, we will represent the function both in terms of x and y.
Then we can find out the coefficients, as I said. Then we can find out the displacement at any point within the element. The selection of displacement function or finding out the displacement function is very essential for finding out the secondary unknowns such as stresses and strains. The next step in FEM is defining the strain displacement and stress strain relationships. The strain displacement and stress strain relationships are necessary for deriving the equations for each finite element. For example, in the case of one-dimensional deformation, say in the x direction, we have strain epsilon x, which is related to the displacement u by the simple formula which is epsilon x equal to du by dx for small strains. In addition, the stresses must be related to the strains through a stress strain law, generally called the constitutive law. And the ability to define the material behavior accurately is most important in obtaining the acceptable results. And we know that the simplest of stress strain laws, which can be often used in stress analysis, is sigma x equal to E into epsilon x, as we know, where E is the modulus of elasticity. Again, for two-dimensional problems and three-dimensional problems, the strain displacement relations may vary, because in two-dimensional problems, there will be strain both in x and y direction. So you're familiar with the equation, which are epsilon x equal to du by dx, epsilon y equal to dou v by dou y, and gamma xy equal to dou u by dou y plus dou v by dou x. So these are the equations in the case of two-dimensional problems. Similarly, we can extend that formulas if you have a three-dimensional problem. So I'll share that formulas for your understanding as a separate file. Similarly, the stress strain relationships for two-dimensional and three-dimensional problems also are different from the basic Hooke's law. That also you might have studied in your AMOS course. I'll share that again as a separate material for your understanding. So in all these cases, as I said, the primary unknown is displacement. So by selecting a displacement function and finding out the constants in the displacement function, we are trying to find out the displacement at an arbitrary point in the element. So once we have the primary unknowns, by using this strain displacement and stress strain relationships, we can find out the secondary unknowns such as strains and stresses.
So now we are on to the next step of FEM, which is called the derivation of elemental stiffness metrics and equations. So we begin with the discretization of the geometry, and we selected the suitable element type. Then we've assumed a variation of displacement function over the element. So that step is called selection of a displacement function. And the third step, we have defined the strain displacement relations and stress strain relationships depending upon the problem. And now we have to find out the stiffness metrics for an element. So once you have find out the stiffness metrics for the element, then if you have two or three elements in the geometry, then I can combine all these elemental stiffness matrices to form the global stiffness matrix. So for that, the initial step is for finding out the elemental stiffness matrix, this K matrix. This K matrix can be found out in a number of ways. One of them is direct equilibrium or stiffness method, and the second method is called work or energy method, and the third of them is called methods of weighted residual. So each of them have its own advantages. For example, the direct equilibrium or the stiffness method is used when we have one-dimensional problems or one-dimensional elements, because that is easily adaptable to one-dimensional elements. In that, we make use of the force equilibrium conditions and the compatibility equations to derive this stiffness matrix. But if we go for work or energy method, then that is commonly used for two and three dimensional elements. In that, we use the principles of virtual work, then the principles of minimum potential energy and Castigliano's theorems for the derivation of elemental stiffness equations. Similarly, we have one more method by which we can find out the stiffness metrics for the element, that is called methods of weighted residual. And that is one of the popular method
inside the weighted residual method is called Galerkin method, and this method gives the same results as of the work or energy method, but wherever the energy methods are applicable, and they are especially useful when the potential energy is not readily available, because to find out the equation for using work or energy method, we need to have the equation for the potential energy. But if you can't find out the equation for potential energy, then it's better to go for methods of weighted residual. And as I said, Galerkin method is one of the commonly used weighted residual method. So by doing all this, what we are trying to get is this matrix. This is called K matrix or the stiffness matrix, which is written as K. And this K matrix is normally a square matrix, square and symmetric matrix. And these force matrix, and this is a force matrix, and it is a column matrix. And this one is a displacement matrix, or a matrix of unknown degrees of freedom, or generalized displacement. So these two are column matrix, and this is a square matrix. So this one, you will understand how we find out this stiffness matrix when we go and see the problems on beam and bar elements. There you will understand clearly the significance of each of this influence coefficient. These are called stiffness influence coefficients. This K11, K12, etc. are called stiffness influence coefficients. And you will understand when we discuss problems on beam and bar element, how this or the values of K11 or K12 are derived. So for the time being, let's keep in mind we have to derive the elemental stiffness matrix, and for that we have number of methods, as I said. Then you can find out the elemental stiffness matrix, and we can formulate this equation for each element. So once we have this equation for each element, then we go to the next step for combining all these equations to form the global stiffness matrix and its equations. So once we establish elemental stiffness equations, then we can combine all these elemental stiffness equations, and we can also apply the boundary conditions which are known to us to form the global equations. Then that equations we will solve it for finding out the unknown degrees of freedom or unknown displacements. So that is what we do in this particular step. We'll assemble all the elemental equations and obtain the global or total equations, and we'll also apply the boundary conditions, so that we'll get an global matrix, and we can solve for the unknown displacements. And we know that in the step 4 we've developed an equations for the elements of the form small f equal to small k into d, where small f is a vector of elemental nodal forces, and k was the elemental stiffness matrix, and d is a vector of unknown elemental nodal degrees of freedom or displacements. So once we find out all the elemental equations, we will combine together and form an equation of the form capital F equal to capital K into D, where capital F is a global nodal forces and capital K is the global or total stiffness matrix, and D will be now the vector of known and unknown degrees of freedom. The reason why I said this is known and unknown degrees of freedom, because here I am applying the boundary conditions. For example, if I take a roller support, I know that a roller support allows displacement only in the x direction, not in the y direction. So I can say that the displacements in the y direction will be 0 for a roller support. Similarly, for a hinge support, I know that it restricts the movement both in the x and y direction. So correspondingly, I can substitute here in the equation that the displacement in the x and y direction is 0. So all that can be done here in this one. So that simplifies the equation, and that will we can solve that equation for finding out only the unknown displacements. So that is what we do in the step 5 of FEM.
Once we find out the unknown degrees of freedom or the displacement from the step 6 of FEM, then we can find out the secondary unknowns such as the elementary strains and stresses. So for the structural stress analysis problem, the important secondary quantities of strain and stresses can be obtained because they can be directly expressed in terms of the displacements determined in step 6. In one of the step or in step 4 of FEM or in step 3 of FEM, I have said that we can establish a relationship between displacement and strain. For example, in one dimensional case, we can say that epsilon x equal to du by dx, where u is the displacement in the x direction. So we can find out the strain in the x direction as epsilon x equal to du by dx. So from there, we can find out the strain in the x direction. And we also can find out the stress in the x direction by using the Hooke's law for one dimensional case, which is sigma x equal to E into epsilon x. So from there, we can find out the stresses as well. So that is what we do in this particular step. We'll find out elemental strains and stresses from the equations that we already defined in the step 3 of FEM. So the last step in FEM is interpretation of the results. So in this, we will interpret and analyze the results to use in the design and analysis process. So we can find out the regions where the deformations are maximum as well as the stresses are maximum in this step of FEM. So here, this particular image over here shows a bicycle wrench after the loading. And here, without the shade or without the color, that represents the initial or the original wrench before the loading condition. So you can see a number of meshes here. So this is now you understand from this figure that initially we have this wrench, and we will divide this wrench into finite number of elements or discretize it with suitable elements. For example, here we've used mostly quadrilateral elements for discretization. So, and after this, we will establish elemental stiffness matrices for each quadrilateral element. Then we will combine all this elemental equations to a global equation, and we will apply the boundary conditions such as where is fixed and etc. Then we can solve for the primary unknowns such as the displacement at each point within the element, and from the displacements we can find out the strains. Then from the strains we can find out the stresses. So once we get the stresses at different points in the element of this wrench, then we can plot the variation of stresses throughout the member. And once we do this, we will obtain that these are the regions where the stresses are maximum, and also here the stresses are maximum, and the blue ones are the regions where the stresses are minimum. So we can say that this is a region where the failure can happen easily. So you will get an idea about by doing the analysis of a model, we will obtain an idea about where the failure can begin and where the deformations can be maximum. So these are basically the main 8 steps which involved in solving an FEM problem. And we will go and see the more details of FEM in the coming presentation.